This is the progress report for the final project. The first paper that I reviewed was Accurate Uncertainties for Deep Learning using Calibrated Regression. I'll be first talking about the need of uncertainty and the Bayesian neural network as a mean to obtain uncertainty, and the need for a calibrated uncertainty and calibration algorithm for regression models that the paper proposes. So the reason why we need model uncertainty is that deep neural networks tends to be overconfident about their predictions, and they do not have the ability to say, I don't know. And this is problematic for applications where silent failures can lead to dramatic outcomes. Um, for example, self-driving cars, medical diagnosis, or finance. And the Bayesian framework provides a way to analyze and train uncertainty-aware neural networks. So to give a brief introduction to Bayesian neural network, a Bayesian neural network is a stochastic artificial neural network trained using Bayesian inference. So instead of having a single weight value, they put a distribution on the weights. So we simulate multiple possible weights, and thus they can be considered as a special case of ensemble learning. And the main motivation of ensemble learning comes from the observation that large set of average performing but independent predictors can lead to better prediction than a single well-performing predictor. However, in Bayesian neural network, this is not their main aim. Rather, the neural network to obtain a better idea of uncertainty associated with the underlying process. So the typical Bayesian inference algorithm is the following. You first define a prior p theta, usually you define as a standard normal Gaussian, and given some training data, you will get the posterior of the weights, so p theta given t. And for n number of times, you draw from this posterior and you run through the neural network with a specific input. So for each input, you will obtain a n number of outputs. And normally your predicted value will be the average of these outputs. And the uncertainty can be quantified by this equation, where it depends on um, the n outputs. And you can get the probability distribution of py given x using these values. However, calculation of posterior is generally intractable, so the two widely used method to overcome this problem is Markov chain Monte Carlo, which is an algorithm that samples from the posterior. However, their lack of scalability have made them less popular for beginners. And the more used method is variational inference, which is a method for learning an approximation of the posterior using variational distribution. So using Bayesian neural network, you can get a uncertainty value um, quantified by the creditable interval. A credible interval is an interval within which an unobserved parameter value falls with a particular probability. So for example, for a 95% credible interval, we should expect that approximately 95% of our observed data fall inside this interval. Um, the So the reason we need a calibrated uncertainty is that calibrated uncertainty means that the credible interval aligns with the observed data. So for a 95% credible interval, if only 80% of the observed data falls within that interval, the uncertainty value is not calibrated. Modern deep neural networks achieve high accuracy but poor calibration compared to shallow networks, and the width and depth and techniques like batch norm um, are known to affect the calibration, negatively affect the calibration, and thus, in order for the uncertainty to be meaningful for the user, we need to calibrate the uncertainty, which is the credible interval, so that it matches the true outcome. So if you see the plot here, this is a uncalibrated uncertainty, and if you can see the observed data, most of the observed data doesn't fall within the credible interval. However, if we calibrate the uncertainty, you can see that the observed data, most of the observed data falls within this credible interval. So it's calibrated. And this paper proposes a extends the recalibration method used for classification tasks such as path scaling to regression. And they propose a procedure that is universally applicable to any regression model. And it does not require modification of the model, since the algorithm is applied to the output of any existing model in a post-processing step. So this is the algorithm they proposes, and the algorithm has two main steps. They first construct a recalibration dataset, and then they train a regression model on this dataset. And now go into detail of the steps. I'm sorry. So the first step of the calibration algorithm is to obtain predictive conditional distribution for each x in the calibration set. So as we said in the Bayesian neural network, for a input x, we can get the PDF py given x. So for all the data in our calibration set, we calculate this PDF, and then the observed y of each data point, denoted by yt, falls somewhere within those conditional distributions. We evaluate the conditional PDF at each observed value of the response y to obtain the predictive quantiles. We next find the empirical quantiles, which are defined as the proportion of observations that have lower quantile values than that of the current observations. The mapping of the predicted quantiles to empirical quantiles will form a recalibration dataset. And this data points represents this recalibration dataset. And if the model was perfectly calibrated, this would have been a perfect straight line. But as you can see, since this model is miscalibrated, this is not a straight line. Step 2 is to train the model on the recalibration dataset and use it to output the actual probability of any given interval. So, for example, if P equals 95%, but only 80 out of 100 observed data falls below the 95% quantile, then we adjust the 95% quantile to 80%. And this is equivalent to saying that we increase the credible interval so that it is the 80% quantile. So as you can see here, this is a 95% quantile, but we adjust it to a 80% quantile, and so that the observed data falls within this 80, so that the observed data are falls in the credible interval. The second paper that I reviewed was PCFairness, a unified framework for measuring causality-based fairness. To give some background, a fair machine learning studies how to develop predictive machine learning models such that the decisions made fairly treat all groups of people, irrespective of their protected attributes such as gender and race. A recent trend is to define fairness as causality-based notions, which concern the causal connections between protected attributes and decisions. A number of causality-based fairness notions have been proposed for capturing fairness, such as total effect on interventions, direct-indirect discrimination on path-specific effects, counterfactual fairness on counterfactual effects. But there's a thing called identifiability, which concerns that whether they can be uniquely measured from observational data. Causality-based fairness notions are defined based on different types of causal effects, and thus their identifiability depends on the identifiability of these causal effects. And this paper proposes a framework for handling different causality-based fairness notions. So to give some definitions of previous frameworks for causality-based fairness, the total causal effect is the total causal effect of the value change of x on y. The path-specific effect is given a causal path, the path-specific effect of the value change of x on y through that path, and it's denoted with this equation. And counterfactual effect is given a factual condition, the counterfactual effect of the value change of x on y. The paper then proposed a path-specific counterfactual fairness, and a path-specific counterfactual effect is given a factual condition and a causal path. The path-specific counterfactual effect of the value change of x on y through that path is given by this equation. And path-specific counterfactual fairness is saying that when it achieves the PCFairness, this value has to be 0. And we also say that we achieve tau PCFairness if this value, the absolute of this value, is less than or equal to tau. So in this section, we defined a unified fairness notions for representing different causality-based fairness notions. And the key component of this notion is a general representation of causal effects. And the paper shows that the previous causality-based fairness notions can be expressed as a special case of the PCFairness, which their connections are summarized in this table. And in addition to unifying the existing notions, the notion of PCFairness also resolves a new type of fairness that the previous notions could not do. One example is this individual direct discrimination. So for measuring this path-specific counterfactual fairness, they develop a general method for bounding the path-specific counterfactual effect in any unidentifiable situation. And they formulate the bounding problem as a constraint optimization problem. And the general idea is to parameterize the causal model and use the observational distribution to impose constraints on the parameters. Then the path-specific counterfactual effect of interest is formulated as a objective function of maximization or minimizations for estimating its upper or lower bound. So before deriving the upper and lower bound, they first introduced a key concept called the response function variable. So if you consider a arbitrary endogenous variable denoted by V, its endogenous parents denoted by PAV, and its exogenous parents denoted by UV, its associated structural function in the causal model denoted by FV, and in general, the exogenous parents can be a variable of any type with any domain size, and the associated structural function can be any functions. So this makes the causal model difficult to handle. However, for each particular UV, the functional mapping from PAV to V is deterministic. Thus, we can map each value of UV to a deterministic response function. And we denote the mapping from UV to RV, the response function, as this. And so we can rewrite this structural function to um, to this equation. And the paper shows how the joint distribution of all the endogenous variable can be expressed as a linear function of PR. And after this kind of steps, the final result is this equation. And PV is expressed as a linear function of PR. So for bounding the path-specific counterfactual effect, they apply this response function to their path-specific counterfactual effect. And I am yet to understand the proof of the steps, but hopefully I can understand it by the final presentation. But the result is that the first term of the counterfactual path-specific counterfactual effect is this equation, and the second term is this equation. And both terms are linear combinations of PR. Express both joint distribution PV and path-specific counterfactual effect as linear functions of PR. All causal models that agree with the distribution of observational data D cannot be distinguished and should be considered in bounding PCFairness. Therefore, finding the lower and upper bound of the path-specific counterfactual effect is equivalent to finding the PR that minimizes or maximizes the path-specific counterfactual effect, subject to that the derived joint distribution PV agrees with the observational distribution PD. So this paper, in conclusion, this paper developed a general framework for measuring causality-based fairness and proposed a unified definition that covers most of previous causality-based fairness notions, namely the path-specific counterfactual fairness. They formulated a linear programming problem to bound PC fairness, which can produce the tightest possible bounds.